Hi, I'm Paul Moran with the Energy Conservatory, and welcome to our webinar titled Multifamily Blower Door Testing. And the focus is primarily going to be on testing new construction, but all of the things we're talking about are certainly applicable to existing buildings also. You can see kind of starting on the left there, we're using for testing individual units. We're using a window frame and a duct blaster fan, and next is what we call our mini blower door system. So it's a blower door system using the duct blaster fan, and then our standard single fan blower door. And then if you're testing whole building single zone testing, then we get into 2 and 3 fan systems, or even multiple 3 fan systems for larger buildings. Some housekeeping issues. If you're having trouble with your audio, go up to the meeting pull down menu and go through the audio setup wizard, and that should take care of the problem. Please type in questions as you're thinking of them, and we will be going through and responding to those during the webinar, and then we'll have a question and answer session at the end. If we don't get to your question, we'll respond to it directly to you by email. All of our webinars, soon after they're done, we record them and make them available on our YouTube site. So you can visit our YouTube site and view all of our past webinars that we've done. And we're always looking for feedback on how you think the webinar went and suggestions for future webinars. We do find that the webinars that are best attended are ones that you've asked for. So please, if there's a topic that we haven't covered already, we'd like to hear from you and put on those type of webinars. This one will be we'll have BPI continuing education units available, one credit for attending the webinar. We won't be giving you a completion certificate, but that information will be loaded onto the BPI site as soon as possible. And I'm sure you're familiar with the regular lag time between when it's completed and when the credits show up. If you haven't provided us with your BPI number, you'll need to do that, certainly. And you need to log into the webinar using the same email address you used when you registered in order to get credit. So you need to be logged in order to get credit. So you can't be watching the webinar on somebody else's computer and expect to get credit. You need to log in yourself in order to get credit. So our agenda today, we're going to start out with commonly used airtightness standards, and then we'll move on to programs requiring testing. Where's the demand out there? Total leakage versus leakage to outside, and this is also referred to as unguarded and guarded testing. We're going to talk about preparing for the test. So that includes setting up the building for the test. And so you're able to do the test in a repeatable way. You know what the building conditions are, so if you come back another time and test it, you're testing it under the same conditions. Setting up the equipment, running the tubing and cabling if you're doing automated testing. We'll cover all those things. Software options for doing the test. And then so we're going to start with the commonly used airtightness standards. Airtightness standards are primarily used in order to do tests in a repeatable way, so you'll get repeatable results. So standards in various levels of detail are referred to talk about how you set up the building for the test. Yeah, and that's certainly an important part of doing the test. And and how the test should be performed. If you're just testing it at 50 pascals, if, how you take a baseline, and how long a period it needs to be, how long the periods of record at each data point need to be, and then how to calculate the accuracy and repeatability of the test. So standards get pretty involved. First one is ASTM E1827, and that's a repeated single point test. And it has two options: a repeated single point test or a repeated 2-point test. And it has you take multiple readings. So you'll do a baseline, and then single point has you test at 50 pascals, and then do another baseline, and then repeat that process 5 times. And then it has specific ways to determine the results of the test and the accuracy of the test based on that data. ASTM E779 is you're testing at multiple data points, 5 data points between 25 and 60, and you're testing both depressurization and pressurization. And then it also has a way to determine what your CFM at 50 is based on all of those data points and how accurate and repeatable that test is. And it talks about certain weather conditions that you can test under, and goes into a lot of detail on doing those calculations. CSGB, Canadian General Standards Board, 149 is a test that's been in Tektite for years and years, and that's an 8-point test, data points from 15 up to 50. And again, it has methods of determining the accuracy or repeatability. All of these standards do require a density correction, so the reading on your DG700 is not corrected for temperature difference between inside and outside the building, and the altitude. So some standards just require a temperature correction, and others require temperature and altitude corrections. ResNet Chapter 8 standard has 3 different options: a single point, repeated single point, or multi-point test. And this is probably the best document, besides maybe the Army Corps standard that refers to E779, on how to set up the building for the test. So it goes into a lot of depth on setting up the building in a repeatable way for doing the test. There are a lot of protocols different protocols that refer to one or more of these standards. So some give you options on which standard you use. Other ones refer to specific standards. So it becomes important if you're going to do tests in a repeatable way that you're following a standard and you're setting it up and taking data in a way that's repeatable. So programs requiring testing: the 2012 International Energy Conservation Code requires residential buildings 3 stories or less be tested. So this will include all multifamily buildings. So if your state has adopted the 2012 code, it requires blower door testing and includes multifamily buildings 3 stories or less. There are at least a dozen states now that either have adopted or will be adopting a code that's at least as stringent as the 2012 code. So it's becoming, more and more popular, and in about I think 4 or 5 states are coming online in 2012, including Minnesota and Iowa, and some others. And we're seeing this more and more around the country where blower door testing is required for new construction as part of code. And most of the United States is in climate zones 3 through 8, 3 through 7 actually, and that's at 3 air changes per hour. Yeah, and there's small parts of the country in the very southern tips of different states that are in zones 1 or 2. So that's at 5 air changes per hour, but most of the country that have adopted the code is 3. And some have adopted, like Illinois, for example, has adopted the 2012 code, but their state said 5 air changes per hour is what they're shooting for to start with. So they're trying to make it more achievable for their builders in Illinois to start with. So there's a map of the states, so you can kind of get an idea of what states near you may be requiring blower door testing. Georgia has also, they adopted the 2009 code, but they did have blower door testing requirements as part of their state code. And I think North Carolina is one that's adopted the 2012 code that isn't colored in this one here. But and the blue ones are dark blue have adopted the 2009, so dark purple 2012, dark blue 2009, light blue 2006, and the states that are gray have not adopted a statewide code yet, but there are cities and communities scattered throughout those states that have adopted codes either 2009 or 2012 that require testing. So programs require testing. The Army Corps of Engineers has required for years that all new military buildings be tested, and they're starting to move towards testing existing buildings also. And that standard is 0.25 CFM at 75, so they're testing at 75 pascals instead of 50, and that's pretty common with bigger buildings, taller buildings. They're testing at 75 pascals instead of 50 because you've got, you know, higher baseline readings and more wind effect on bigger buildings. And it's based on square foot of enclosure area, which really makes a lot more sense than air changes per hour, because buildings leak at the enclosure area, not based on volume. Volume is a good standard for calculating ventilation, but that I think is primarily why air changes per hour as an airtightness standard started out. It started out that way because ventilation was being calculated based on volume, but building leaks on its enclosure area, and that makes a lot more sense. And you'll find, depending on the shape of the building, there really is not a good correlation between square foot of surface area and volume. So more and more standards are moving towards enclosure area rather than volume for their standards. So 0.25 CFM 75 is approximately equivalent to 0.19 CFM at 50. So you get an idea. Some standards are CFM 50, some are CFM 75. So if you want to do a direct comparison, 0.19 CFM 50 is what the Army Corps standard would be equivalent to. But they're finding that if the contractor is paying attention to the details right from the design phase through the construction phase through the testing phase, that the average is actually about 0.11, so twice as tight as that standard. So they're finding that 0.25 is a very achievable standard, and if you're really paying attention to details, it should be more than twice that tight. So that's typically the way that standards start out, is when they're first enacted. They give people a lot of leeway, and then as years go on and they get more experience, they start tightening it up. It refers to E779. as a testing protocol. They've adapted it a little bit. They're requiring 8 data points instead of 5, or 10 data points instead of 5. Excuse me. They're referring to ASTM E779 requiring 10 data points instead of 5, and they give you a little more leeway as far as what temperatures and weather conditions, wind conditions you can do the test on. So that makes it more able to do the test. If you're shipping a bunch of equipment out to do a test on a given date, you want to be able to do it within a day or two. You don't want to have to wait for weeks for the weather conditions to change. You certainly don't want to test during a hurricane, but you want to test on as many variety of weather conditions as you can. Energy Star for high rise is a compartmentalization test, so you're testing unit by unit. And that standard is 0.3 CFM per square foot of enclosure area with adjacent units open to the outside. So you're seeing 50 pascals across all surfaces during that test. And they give you options, either test either the E779 standard or the E1827 standard. Sampling protocol may be used, so you don't need to test every unit, but they have they're following the resonant sampling protocol as to how that can be done without having to test every unit. And they want preliminary and final testing. So when the first couple of units are ready to test, excuse me, they'll want you to get in there and do those tests right away. And that makes a lot of sense, even on a low-rise building where it's up to 3 units. You'll be starting out, once the first floor, they start sheetrocking on the first floor. On the second floor, they may be finishing up mechanicals and it might not be insulated yet. And on the third floor, they're probably just starting on mechanicals, and then they move on up. So if you wait till the building is complete before testing, that's not really setting up your customer to pass the test. You need to get in there as soon as a couple of units are available, find where the issues are so they can be corrected right away before the rest of the units are sheetrocked, and on the other floors work through those details as you're going up. So and they do require, if you're the consultant on the project, you're involved in the design phase and during construction phase, and then the testing phase also. So it's a pretty comprehensive protocol designed to get good results. So you're getting them to pass. So hopefully they get you involved early on in the process. There's certainly a lot of stories out there about when they decide to get Energy Star status after the building is half done, or maybe even completed, and your likelihood of success are a lot less under those conditions. LEED has a multifamily mid-rise program that as a prerequisite requires testing, and that's based on square foot of surface area, again 0.3 CFM at 50 per square foot of surface area, and that's prerequisite, so that's required if you're getting that. And then also they have you can get credits for air tightness also. If you get it tighter than 0.224 CFM per square foot of surface area, you can get credits for it. And it follows the Energy Star high-rise protocol, so it refers to that, so you know what steps to follow for that. Washington State has had requirements for testing all buildings greater than 3 stories for a number of years, and It's mainly enforced in the Seattle area, and it's 0.4 CFM per square foot of surface area, so they give you a little bit of leeway. And if they are in the Seattle area, they are allowing buildings to pass as long as, if it fails the test and you make a good faith effort to air seal it, they're letting it pass without achieving that 0.4. They're trying to make this an achievable standard when they're starting out, and they've had pretty good successes out there with testing large buildings. You can do HERS ratings on multifamily units, and we're going to be going into that in more detail as we go through here. There are state and utility multifamily programs that have incentives and rebates for doing blower door testing on multifamily buildings. Green Communities is a program that if you're getting your funding through green utilities, you have to follow their protocol for in most states that requires blower door testing. In some they've made exceptions, and if buildings are going through a major rehab, some of them do require meeting Energy Star, and other ones are requiring blower door tests, but not Energy Star. Weatherization programs, it varies state by state how much blower door testing they do with the multifamily programs. A lot of states, not a lot of states, but some states do require blower door testing if you're weatherizing multifamily buildings, and depending on what type of building it is, it certainly makes sense, especially if you're doing buildings with pitch roofs where you can get in the attic and do air sealing. It makes a lot of sense for programs to do that, to help find where the leakage pathways are and diagnose the air leakage issues, and also as part of confirming that the work was done properly. Our testing options are going to be dependent on what type of building we have, and we'll start out with townhome type units or row house type units, where our only entrance to the unit is through a exterior door going into each unit, so there's no common condition hallway. And we'll set up a blower door or duct blaster fan in a window on unit number 1, and we'll depressurize that unit. And to get a repeatable test, we're going to have control over units 2 and 3 also. We want to make sure there aren't exhaust devices running in those units or open windows or doors in those units, because that will affect the repeatability of our test. Oops. Another option is to set up a fan in unit number 2 also and depressurize that unit. And when we do that, because each unit is at the same pressure, now there won't be air movement across that partition wall between the units, because remember, we need a driving force and a hole before we get airflow. And if we've got same pressure in each unit, we've taken away the driving force, so there isn't any air movement across those holes. So we're in this type of test, we're doing a test on what's called a guarded test, or a leakaged outside test on unit number 1. So we've got unit 1 guarded, and we'll get a CFM to the outside just on unit 1 on this type of test. So let's assume this is just a 3 unit building, and we set up a fan also in unit number 3 and bring that up to pressure. Now we're doing a fully guarded test on all 3 units, where the leakage through the fans, our CFM readings through our fans is actually the leakaged outside number for each of those units. And we can add those 3 together to get the leakage for the entire building. Apartment buildings give you more options how to test, and certainly will get more complicated. And we can see we've got a floor plan of a 6-unit building, and let's say it's 3 stories tall. We can see there's stairways and doors to the outside at each end of the building, and we've got a common conditioned hallway. So let's say we set up, we're on the middle floor, and we're setting up in the door to the hallway. And as you can see, we've got doors open into the hallway and doors open to the outside. So we've got conditions now where we've got control of the building, mechanical systems are off. We've got all adjacent spaces on the floor above and floor below, so they're open to the outside. So we'll get a common pressure across all of those openings, and we've got our fan running. So if we want to do a guarded test where we're going to guard all adjacent spaces, we would have set up one on the left side and bring that up to pressure, one on the right side, bring that up to pressure. We could set one up in the hallway and bring the hallway to pressure because that's an adjacent space too. And then we would also set up a fan above and below. So in this case, we'd need 1, 2, 3, 4, one above and below would be 5, 6 fans to keep all adjacent spaces up to pressure. And there still could be leakage even under this condition, depending on our floor joist and ceiling joist configuration. We could even under this condition have air moving from this space through the floor joist or ceiling joist into adjacent spaces across the way. So it gets complicated, and even though we go through the trouble of setting up all those fans, we might not have ideal repeatable test conditions. ResNet in August of 2014 came out with some guidelines for doing multifamily energy ratings, and at this point they only allow energy rating at the unit level. So, but this guideline is really intended for all types of buildings, whether you're doing ratings or not. It's a good, well-written guidance document for a first draft on how to test multifamily buildings. It is just a voluntary guideline. It hasn't gone through peer review and is not a standard. It's simply a voluntary guideline, but it gives you something if you're doing tests and you want to do it in a repeatable way. It gives you guidance on gives you choices and gives you guidance on how to set up and do the test. So I think it's worth going over these. It has 4 separate protocols. The first one is an unguarded dwelling unit blower test, or it's often referred to as a compartmentalization test. So with this type of test, we're setting up a fan to the hallway, or it could be a fan in a window, and depressurizing that unit. And it wants adjacent spaces to be open to the outdoors or be at least 90% of the test pressure. So if you're testing at 50 pascals, all the adjacent spaces will need to be at least 45 pascals, within 10% of the induced pressure. So we're showing doors open to the adjacent spaces and to the outside during that type of compartmentalization test. So we're again, this would be referred to as a compartmentalization test, or a total leakage test, or an unguarded test. There are certainly a lot of advantages to compartmentalizing units. It'll reduce sound transfer, and that becomes very important in a dwelling like this. Reduces odor and pollutant transfer. Reduces wind effect. If you get the wind blowing on the outside wall, air will have to leak from that unit to the hallway, and then the hallway to the adjacent unit, and the adjacent unit to the outside. And by compartmentalizing, you can greatly reduce that wind effect. And stack effect the same way. If you do a good job of air sealing between floors to compartmentalize that space, it reduces the amount of air leakage due to stack effect. Allows you to be able to control mechanical ventilation much better, certainly also. If you do a really good job at tightening the outside walls and don't pay attention to the walls between units, you're certainly going to have indoor air quality problems, and it's going to be hard to control the stack effect and wind effect and mechanical ventilation in the building. In new construction, this can be done by sealing the bottom plate to the floor, sealing sheetrock at the edges with acoustical sealant at an airtight drywall approach, where you're sealing to the top plate, you're sealing to the bottom plate, and at the outside edges of the walls, at partitions and partition walls and exterior walls, you're going to seal that to make that sheetrock airtight, and then use the flanged or gasketed cable boxes, electrical boxes and cable boxes to make that airtight. Especially with buildings that are framed with metal studs, where all the studs have knockouts to get cabling through or plumbing through. If it leaks in one place, it leaks everywhere. If you try doing blower door guided air sealing, everything you check leaks, whether it's trim on an interior door or a light switch or electrical outlet or cable outlet on an interior wall. Everything is going to leak. So doing that airtight drywall approach goes a long ways towards making that building much more compartmentalized. Second option of the 4 protocols is doing a full building single zone blower door test. So that's pretty obvious and pretty straightforward. You just set it up in single family type conditions where you prop open all the interior doors and bring the whole building up to pressure. And you can test, if you figure at 3 air changes per hour, you can test, you'd be able to test this building if the units were, say, 700 or 800 square feet. You'd be able to test an 18 unit building with one blower door fan. So you can test with a 3 fan system. You can test a pretty large building in this process. You can't use the results of this for a rating, so you can't interpolate what the CFM would be of each unit based on square footage or anything like that. This is simply a single zone blower door test as an option for testing a building, but it couldn't be used at this time for doing an energy rating on an apartment building. So the next option is a full building multi-zone blower door test. So this is in reference to doing a townhome type building. It could be townhome row house, could be what's referred to in some parts of the country as a garden style building, where all of the units have only doors to the exterior, but they're open to unconditioned exterior spaces. So you might have a 3-story building with units back to back, and you can only get in those units from exterior doors. So for this, you have to do you have to set up a fan in each unit and test the whole building at once. So if you had a 24 unit building, you would need 24 fans set up. So that gets away from issues of if you've got a crawl space in an attic space above the units, you get, you turn on blower door fans in units 1 and 2, and you'll get leakage to the attic and connection with unit 3 through attic spaces or floor spaces. So it's sometimes referred to as a fully guarded test, where you've got a blower door fan on every unit and you're testing the whole unit. So if you add all those blower doors together, you get leakage to the outside of the entire building, and the air moving through each of those fans is the leakage outside of each of those units. But it does specify that it needs to be a full building test. Fourth option is an interesting option that really speeds up the testing process and gives you better results. So this is called a full building blower door test, while simultaneously with a target dwelling unit. So the way we do this is we set up a fan either in a door or a window of an individual dwelling unit, and then we're also depressurizing the entire building. So we're using the blower door going to the outside to depressurize the whole building, and then we've got a fan running on that individual unit. So when we depressurize the entire building and bring this unit up to pressure, it's like a duct leakage outside test. Those of you who are familiar with doing that type of test. So this fan is cruising zero pressure to the conditioned space. We're keeping this at the same pressure as the rest of the building during the test, and then there'll be no leakage to any of the adjoining spaces, and the air moving through this fan is only the leakage to the outside for that dwelling unit. So with this type of test, if you can set up in the hallway with your gauge in the hallway and your tubing out in the hallway, and you can be connected to an electrical outlet in the hallway, and you can just cruise the fan at 50 pascals for the main part of the building, and then just pick up and go unit to unit to unit to unit, and pretty quickly do guarded tests on every unit with this method, with the main fan cruising 50. So those are four options for doing that type of test. Next, I'm going to use a simulator to do tests on a 4-unit townhouse type building, and these are the leakage to the outside and to adjoining spaces are based on an actual building. So the default that I'll be using with this simulator are based on an actual test. Okay, so here's our simulator. So I'm going to start out with, so we've got unit 1, 2, 3, 4. We've got a blower door set up on each one. And I'm going to set unit number 1 to cruise 50. And I'll write down these numbers. So we're going to compare testing one unit at a time, or an unguarded total leakage test. And we're going to compare those numbers with what happens if we test all 4 at the same time. So we can see when we turn this on, we're at 1371, and our adjacent spaces pressure changes. We're at 8.5 pascals, the adjoining unit, 3.1. The next unit over, unit 3, unit 4, changes by a little bit also. So we've got air movement going through all 3 of those units. So then testing unit 2. The pressures change, you can see in the adjoining spaces, and we're at 1157 with unit 2. I'll write that down. Unit 3, we're at 1424. And again, you can see adjacent spaces. This one changed by almost 11 pascal, so there's really a big connection there. We'll turn that fan off, and then unit 4, we're at 1348. All right, so I've got those 4 numbers, so now I'll set all the rest of them to cruise 50. It'll take a little while for that to settle out. Okay, that looks pretty settled. All right, and then I'll write what our numbers were. We're 1371 was the unguarded. 1157. Hope you can read that. 114, 24, and 1348. So unit 1, we're at 1370. We're at 1095 now, and it was 1371 with only the fan on in that unit. Unit 2, we're at 548 compared to 1157, so a huge change there. 855 on Unit 3 compared to 1424. 1084 compared to 1348. So pretty dramatic difference there. So let's bring up, we've got a spreadsheet. There we go. So these are our numbers here. So we're showing when we did the unguarded test, the total duct leakage test, 1 unit at a time, compared to our guarded test with all 4 fans running, and the difference between those two. So you're kind of getting a feel for what we've got here unguarded for all 4 units, and then the total and the difference. So we can see our 2 outside units changed by about 20%, and our inside units, where they're connected now on both sides, changed by about twice that. And the total, if we add all those numbers together, it's about 32% leakier total leakage compared to leakage to the outside. So pretty dramatic differences. And then we can see a lot from this too. This is showing when we're testing unit 1, what are the pressures in the adjoining spaces. So we can see the numbers are biggest when we test unit 1 and look at unit 2, or when we test unit 3 and look at unit 2. So you can, once we get this up on our YouTube site, you can look at this again, and it's interesting to see how these pressures change. Where we test unit 1, our adjacent unit's at 8.5. If we test unit 2, that pressure across that same space is different. It's at 6.3. So some interesting things go on when you measure pressures to adjacent spaces, and it's kind of hard to grasp this chart to begin with, but as you look, as you get a chance to look at it more closely, it's easier to understand. So let's go back to our PowerPoint here. Okay, that's where we were. So now we'll talk about our tubing connections. So now we're kind of getting into the setup. How do we talk about where we set up fans, but now how are we going to make our tubing connections, and then after that we'll talk about making cabling connections if we're doing automated testing. So let's say the gauge is inside the unit, and we're testing in either a door or a window. We'll set up like we're used to for a regular blower door test. We'll run a tube to the outside and a tube to the fan. That changes if we've got our gauges outside the unit, and there are certainly advantages to having the gauges on the outside of a unit. Let's say you're testing a 3-unit building and you set up with the gauges outside. You could, with one person, do this test. So you could set each one up to cruise, enter the baseline in each gauge and set each one up to cruise 50, and let them settle out for a bit and push long-term average on each gauge and write down the numbers. So you could feasibly do this test with one person if the gauge is outside the unit. But our tubing connections are a little different. We have to think a little bit more about what we're measuring when we're doing this. When we have our gauge on the inside, remember what we're measuring is we're measuring the house with respect outside, right? House to outside. We're used to just running the green tube to the outside and not worrying about the input, but the input becomes more important and you have to think a little bit more about what you're measuring. On channel B, we're measuring the pressure at the flow sensor of the fan. So we're actually measuring a pressure and the gauge is converting it to flow. We're measuring the pressure at the flow sensor of the fan with respect to the space that flow sensor is in. So the gauge and the flow sensor are in the same space, so we don't need to connect a tube to there. But now when our gauge is outside, we need to think a little bit more about that. We need to measure house with respect outside. We're outside, so we don't need a tube on the reference, but we do need a tube on the input. So we need a tube going into the house with reference to outside. In channel B, we connect our red tube to the fan the way we always do, but we need to be measuring the pressure at the flow sensor with respect to the space it's in. And when we're doing this test, if we're doing a depressurization test, our rings are inside. Our rings are inside the building. So we need to reference the inside of the building with that tube. So either we could connect an additional tube, or we could do a T connection and run one tube to the inside from those two locations. So so will save us also save us some time if we're testing an apartment building and we've got a common condition hallway. We could test from the hallway then, and then easily move from unit to unit if we've got our gauge outside in the hallway. But we have to think a little more about what our tubing connections are and make sure we got that right. So now if we're doing, we talked about that fully guarded test where we're controlling multiple fans, or maybe it's just one fan to get the whole building at a common pressure, and then we're testing unit by unit individually to get leakage to the outside for each unit. So how would we set up the tubing connections for this? First, we're gonna we're dealing with these fans now. We're not worried about the flow through these fans during this test. We're just using the gauge to get this to cruise this fan at a certain pressure. So we need to run a tube to the outside. And if we're using multiple fans, one thing we need to do is now we're in an area where there's a lot of turbulence, and we don't want to leave any taps open, or we'll get some pretty big fluctuations in that area. So we need to add a tube and get it to a calmer part of the building where we're not going to see as much turbulence. So we're gonna we're going to run a tube into an adjacent space. So on channel A, we're measuring house, or building with respect to outside, but we're just connecting a tube there to get it into an area where it's less turbulent. And then we're gonna use the fan control cable, because we're gonna use crews, and we're gonna connect that. Let's say this is a big enough building where we need 3 fans to get it up to pressure. We're gonna connect that fan control cable to the top fan, and we're gonna run 2 fans wide open, and then we're gonna cruise the speed on the top fan to keep it at 50 pascals while we're going around unit by unit. So that's how we want to set up and do that test. So the way we would do that is we would do our baseline, and then we'd uncap the bottom fan and turn it all the way up. And then the second fan, we'll get the blade spinning on it before we take the rings off. Otherwise, if we took the rings off with the fans not going, with the blades not going, the blades would spin backwards, and turning it up wouldn't get it to stop and turn around. So we need to get the blades spinning before we take the rings off to make sure that the blades don't start spinning backwards. And then we'll turn that one up all the way. And then on the third fan, we'll use the speed controller to get those blades spinning, and then we'll uncap that fan to make sure the blades aren't spinning backwards, and then we'll set that gauge to cruise 50 pascals, and we'll have to remember to turn that speed controller back all the way down to make sure that we're accurately getting our cruise number. Remember, we need to be in the just on position in order for that cruise to function properly. An easier way to do that, now that I think about it, would be to set that third fan to cruise 50, and that will get the blades spinning. So set the gauge to cruise 50 before you take the rings off, and wait until you can hear those blades spinning pretty fast, and then take the appropriate ring off of the fan and let that cruise 50. Okay, so then we need to connect our channel B to our fan on our dwelling unit, our test unit. And then on this one, we're using that T connection. Remember, we need the fan pressure with respect to the space it's in, and we need to be measuring house with respect to building on channel B. So what we're going to do, like when we're doing a duct leakage outside test, we're going to want to get this fan at the same pressure as the rest of the building. So the building's at 50, we want this unit at the same pressure, so we're going to be shooting for 0 pressure in that unit. And again, this hallway can be very turbulent. It might not be if we're a ways away from these fans. This area is probably going to be a less turbulent, and we might not need to cap that or leave that tap. If it is really turbulent, we're not going to want to have that tap open, and we're going to want to run it to the adjacent hallway. But in this case, we might be far enough away from that fan, so the air really isn't too turbulent in that space. But just as a precaution, it's a good idea to be measuring in the same pressure zone that we're measuring our outdoor reference with. So now we've got our tubing connection set up. Another thing that we can do to make sure the building is at 50 when we take our readings is we can add a Wi-Fi link to our DG700 that's cruising our outside pressure, and then with our phone we can use the iTech 700 app to see what the building pressure is and make sure it's at 50 pascals when we take our reading. So that way, the fans are noisy, and if you're trying to communicate with another person doing the test, this is just another way to to quickly check and make sure you're at 50 when you're taking your reading on that unit. Using software certainly can simplify the test and simplify the gathering of data. That's what software is really good at, is having a good record of your entire test. And you can always go back and look at it and process it and gather the numbers after the test is done. You'll certainly want to verify before the test day is done that you've got good data, and software allows you to do all of that. When we're using software, we have to make a connection between the DG700 and our computer. So our computer can control the fans and see all of the pressures. And our gauges that are newer than November 2009 have a USB communications port. And it comes with a 15-foot cable. USB is restricted to about 15 feet unless you have special cables that have repeaters in them, and people have successfully run longer than 15-foot cables while doing testing. But just so you're aware of the some of the limitations of the USB port. Another option is using the serial communication port. These are old school communication, but there are definitely advantages to them. We've run 3,000 feet of cable and not had any problem with signal loss. So that's one nice thing about serial communication is you're pretty much unlimited how long a cable you can use and get good solid communication. You can use regular communication cable. It needs to be a straight through cable. And those are available in 6 or 15 or 25 or 50 or 100-foot lengths. So you can buy them with the ends on at various lengths, and they're readily available. And then you'll need a serial. Most computers don't have serial 9-pin serial communication ports, so you'll likely need a serial to USB adapter. We do have serial to Cat5 adapters that we sell, and those can be used with Cat5 cable, regular computer cable, to run as long a length as you want, and that cable is readily available. We do recommend using stranded rather than single conductor cable if you're going to be using it multiple times. The single conductor is what's sold at most big box stores, and that works fine if you're just running it through an attic or through a house and you're not going to be rolling it up again. But it's hard to roll up, and it's more fragile. You're more likely to break those single conductor cables. So stranded is a better alternative, easier to roll up, and more durable if you're using it for this purpose. And then again, you'd need a serial to USB adapter. And remember, these adapters need drivers. So if you need to load the driver on your computer, and if you get a new computer, make sure you haven't lost that driver. You can usually go to a website and find the drivers pretty easily, but remember, those kind of adapters do need drivers. If you're using multiple gauges, you'll need a USB to serial port hub, and those are available. 2-port, 4-port, 8-port. We do sell a 8-port hub for connecting 8 DG700s to the cable. So using that combination of 9-pin serial to Cat5 adapters, and then long lengths of cable running back to your home base where you're controlling all the fans works great. Wi-Fi is certainly another option. Our Wi-Fi link is available now, and you can only connect it sends out a Wi-Fi signal, and your DG700 with the serial number will show up as one of the Wi-Fi networks. So you don't need to connect to the internet or to a router in a house. When you're using the Wi-Fi link, you can make, if you're just connecting with one gauge, you make a direct connection from that link that's broadcasting a signal, and it will show up as a network, and you connect to that, and the first time you connect to it, you need to enter a serial number like you do connecting to any network for the first time, and then it remembers it after that. If you're connecting with multiple gauges, you need to put that Wi-Fi link in router mode, and the Wi-Fi link comes with instructions on how to do that. And you need to associate that each of those Wi-Fi links with that router, and then you make a single connection between that router and your computer, and then you can talk to as many gauges as you want that way. We've used it on pretty complicated big buildings. This one that I'm showing was a gigantic warehouse building that had a concrete block wall with only one door opening between the front and back half, and then had in the front area had an office space and a kitchen area that had concrete block walls with one door opening also. So what we did was use multiple routers and formed a network of routers. So we did have to run a Cat5 cable from the satellite routers to the main router, and then a cable from the main router to the computer. But this router, the main router, was communicating with three fan systems. The back one was, we had line of sight. You want to, for best case scenario, you want line of sight between where the router is and where all the gauges are, and we were able to do this test flawlessly. It's not really wireless. There are still wires, but you still end up running a lot less cabling to make this work. This is aero insulation out in the Seattle, Washington area, and it just kind of gives you a snapshot of how they have their truck set up. With they leave their frames all put together with the nylon panels on and stack them up against the wall, and have all the blower door fans and accessory bags, and they're geared up and ready to go. They test a lot of townhouse garden style apartment type buildings is kind of their specialty. So when you're using software, you can get by with only 2 DG700s, because remember, we've got in the software we can tell it whether it's a pressure or a flow, and we have 3 options for pressures. If it's an envelope pressure, if it's measuring a building with respect to outside pressure, we call that an envelope pressure. It could be an interior pressure, where you're monitoring interior pressures to make sure they're within 10% of the induced pressure. We call those interior pressures, and then that'll show up on a report to document that all your interior pressures were within 10%. And then we've got just a generic pressure. So maybe you want to be measuring an attic or garage pressure during the test, but that's not a pressure that needs to be within 10% of the induced pressure. So you've got 3 options for pressures, and then depending on which fan you're using, Model 3 or duct blaster fan, you have the option of setting up each channel that way. So you record and record the serial number and the way each channel is set up. So gauge number 1, we're using like we would if it was a single fan test. So channel A is our envelope pressure, our housed outside pressure, and channel B is our bottom fan. So you'd set up the first gauge like you would a regular for a regular single fan test. And then the second gauge will be channel A is the middle fan, channel B is the top fan. So that's pretty obvious. Set up channel A the way you always do for a single fan blower door test, and then middle fan channel A, top fan channel B. And then with the 3-fan system, we also have a controller board where you can attach all 3 of your controllers on that one controller board. And this just makes it a lot slicker setup, where you don't have tubing and cabling and extension cords and everything running all over the place. They're just in one central location. So obviously the bottom controller for the bottom fan, middle for middle, top for top. And again, as I mentioned before, we don't want to leave any taps open. So we've got tubing connected to all of the taps because we're in a turbulent airflow area in this location. And we want fans plugged into separate circuits so we don't blow breakers. We use a 3-way fan splitter. So we're splitting our signal off one DG700, and we've got a 4-foot cable here, and we're running that down and plugging it into the 3 controllers. In the software, we've got a master controller that gives the same signal to all of the fans. So every gauge is getting a signal that's the same. So if we have a 3-fan system set up in a building, they're all going to be ramping up at the same speed. And typically we don't use, when we're doing big building testing, we don't use the rings at all. We have a red nylon shower cap type thing to cap the fans rather than using the rings to cap the fans, and we just run all the fans wide open. And if we need if we're getting low fan pressure at the fans, then we'll cap one fan and shut off the controller to it. So rather than using rings, we just start shutting fans down. It's a lot easier to keep track of than which fan did I put that ring on, and keeping track of those kinds of things. So the 3 controller board, we talked about that. We also have as an option, because of those 9 pins, our gauge signal only uses 3 of them. We can combine the signal from 2 DG700s over 1 cable, but then we need to split that back out at the hub, so we've got 1 signal from each gauge split out again. But this does allow us to run, if we're running 250 feet of cable, it's easier to run 1 cable instead of 2 when we're testing larger buildings. So that's an option. And the way we test fan circuits is using a kilowatt meter. Many of you may be familiar with this, or some kind of a watt meter that'll read out in voltage. So we're looking at the voltage. So we're going to plug in our first fan and run an extension cord for our second fan, and we'll plug the kilowatt meter into that second extension cord, and we'll be reading the voltage, and it's usually going to be around 120 volts. And then we'll crank up the first fan and see if the voltage changes on the second one, and if it changes by more than a couple of volts, few volts, then we know. If it goes down by more than a few volts, we'll know they're on the same circuit. We'll have to run a cord to a different one, and then we test the third one that same way against the first and second.